Hey guys, this week we are going to talk about 3.7 in the textbook, implicit functions. And what we're going to learn how to do is we're going to learn how to differentiate implicit functions, which are functions that are not defined in terms of one variable. So let's get started with this. Firstly, an explicit function, opposite of an implicit function, is just a function that we're used to, written in the form y equals f of x. So for example, the function y equals 3x minus 4 is explicit because the dependent variable y is written solely in terms of the independent variable x. Okay, so that is an explicit function. On the other hand, we have implicit functions, and those are functions which are written in terms of both dependent and independent variables. And the reason that we do this is because, sometimes these guys fail to be functions altogether, and we're going to see why that's the case in just a moment. So we have these two examples. The second one in particular is interesting because this is an equation of a circle. So let's get into this. We have an equation of a circle, an implicit function, x squared plus y squared equals 4. Notice that y is not isolated, so this is an implicit function. And we can represent this as a circle centered at the origin with a radius of 2. Why is that? Well, because the formula for a circle is x minus h squared plus y minus k squared equals r squared. So this is the formula of a circle. And h and k, so h comma k, is the center of the circle. And so in this case, our center is 0, 0. So anyway, here we have an implicit function. And let's think about the derivative of this circle. So what's the derivative? Well, we're finding the slopes at every tangent line to every point on the circle. So let's try to do this explicitly. So we start out with x squared plus y squared equals 4. And what I want to do first is I want to get this in terms of y and then differentiate, and we're going to see what happens here. So let's go ahead and subtract x squared from both sides, and we end up getting y squared equals 4 minus x squared. And what I can do now is I can take the square root of both sides, and remember, when I take the square root, I have to tack on a plus and minus sign. So this is going to be, what we end up getting is y equals plus or minus the square root of 4 minus x squared. So let's go ahead and take the derivative. So I have to use the chain rule because I have a function, an outer function square root of x and an inner function. And what's inside of the square root is 4 minus x squared. So I need to use the chain rule, and so the chain rule, I can write this as, before I differentiate this, I can write this as 4 minus x squared to the 1/2, and then using the chain rule, I differentiate the outside, which is just 1/2, 4 minus x squared to the negative 1/2, times the derivative of the inside. Well, the derivative of 4 minus x squared is just going to be negative 2x. And remember, this is very important. This plus or minus is going to stay down there with it. So if I clean this up just a little bit, I'm noticing this negative 2 multiplied by 1/2 is just going to give me negative 1. And so what I have is plus or minus negative 1x times 4 minus, and maybe I'll even write this like this, negative x over the square root of 4 minus x squared. So this is my derivative written explicitly. But let's consider what happens if we choose an x value. So for instance, what if I choose, let's see, what if I choose the following? What if I choose x equals 1? What if I choose x equals 1? Well, that's going to tell me the slope at x equals 1 is going to be plus or minus -1 over the square root of 4 minus 1 squared, which ends up giving us plus or minus -1 over the square root of 3. Okay, and so the point here is that we have two slopes, okay, which isn't great, right? Because which one do we pick? So the first slope is a positive slope, okay? The first slope, so first slope is positive. That's going to just give us 1 over the square root of 3, those double negatives. And the second slope is negative because this plus times the minus is going to give us a net result of a negative. So we have two slopes at x equals 1, and let's take a look at the picture. So where's x equals 1? Well, x equals 1 is right here, but also the curve is going to happen right here when x equals 1. And we can see that this is our negative slope, which was -1 over root 3. And this guy down here is going to represent our positive slope, which was +1 over root 3. And so to kind of deal with, what slope do we pick, we are going to instead differentiate this thing implicitly, and I'm going to teach you how. And that way we'll only get one answer because our derivative is going to be in terms of both x and y, right? Not just in terms of x, because as we can see, if something that we're trying to differentiate is not a function, we're going to end up getting two different answers. But when we differentiate implicitly, we'll only get one answer. So let me show you how to do this. So I'm going to actually show you how to do it first and why it works second. So the way that we do this is we take the derivative of both sides, but anytime we're differentiating a y, we need to tack on dy dx, and that's what we want to solve for. So we want to isolate dy dx. That's what we want to do. So, and again, I'm going to explain more, the why behind this in just a second, but let's go ahead and differentiate this. So if I use the power rule here, I just get 2x. If I use the power rule here, I get 2y, but since I differentiated something with a y, I need to tack on a dy dx. And of course, if I differentiate a constant, it's going to be 0. The next thing I want to do is I want to isolate dy dx by first subtracting 2x on both sides. And so I get 2 times y dy dx equals -2x. And the last thing I'm going to do is divide both sides by 2y to get that dy dx by itself. And so what I end up getting is my derivative of y with respect to x, dy dx, is -x over y. So this is good because we don't have any plus or minus business to deal with. All we have to do is plug in our x and our y. So, that gets rid of the ambiguity. So for instance, if we go back to our x equals 1 example, well, do I mean x equals 1, y equals, what is it? Square root of 3? Do I mean that? Or do I mean x equals 1, y equals negative square root of 3. Which one do I mean? And so, so which one do we mean? What x and y do we want to pick? I'll pick the bottom quadrant. Let's say x equals 1 and y equals negative root 3. So the derivative dy dx is just equal to negative 1 over negative root 3, which is going to simplify to a net, a positive because we have the double negatives. This is our slope. So that's how we deal with that, with these implicit functions that are not really functions when we define them explicitly. We take the derivative, and the derivative should be in more than one variable. So why does this work? So what is this implicit differentiation business, this tacking on the dy dx? Well, the reason that it works is because of the chain rule. Okay, so remember the chain rule tells us that we take the derivative of the outside and multiply by the derivative of the inside. So what we're assuming here is that y is a function of x. So let's just say, for instance, that y is equal to f of x. We could call it y of x or whatever, but I just like the f of x. So if we replace that in our equation that we have, we get this. Right? And so what we can do is we can take the derivative of both sides with respect to x. All right? So if we take the derivative of both sides, well, if I take the derivative of a sum, it's just the sum of the derivatives. So we have d dx x squared plus d dx f of x squared. And on the right side, I'm just going to kind of knock this out. This is equal to 0. Okay, so when I take the derivative of x squared with respect to x by the power rule, that's just going to give me 2x, which is pretty normal. But what happens here? Well, I have to use the chain rule because I have an inner function and an outer function, right? So my outer function is x squared, my inner function is f of x. And so using the chain rule, what I end up getting is 2 f of x to the first times the derivative of the inside, which is f prime of x. Well, since y is just f of x, f prime of x is dy dx, the derivative of y with respect to x. And so we can kind of, replace that here with dy dx. And of course, we defined y to equal f of x. So if I go back and replace that with y, what I end up getting is 2x plus 2y dy dx. Okay, so that is, this all comes from the chain rule, essentially. That's why this works. And so what I want to do now is just do a bunch of examples to kind of, get you used to this idea of differentiating implicitly. So let's go ahead and do some examples. Find dy dx for the square root of x equals 16 square root of y. So right off the bat, I'm going to write this as x to the 1/2 equals 16 y to the 1/2. Well, I can differentiate both sides of this equation using the power rule. The x, I just bring that to the front, 1/2, x to the negative 1/2, boom, done. The second one, remember, this is a y, so I have to tack on a dy dx at the end after I do the power rule. So I can do 16 times 1/2 gives me 8, y to the negative 1/2, dy dx, okay, because I'm differentiating a term with y in it. And then the last thing I'm going to do is I'm going to isolate the dy dx by dividing both sides by 8y to the negative 1/2. And so this is going to be our dy dx. Okay, so that's my derivative. All right, and now we have another weird looking function like this. So let's go term by term. The derivative of x to the 3 is 3x squared. Now, right here, I have to use the product rule because my first function is 5x squared times my second function is y. So, okay, so here we go. Keep the first times the derivative of the second. What's the derivative of y? Just 1. But since I differentiated something with a y, I need to tack on a dy dx. All right, keep the first times the derivative of the second. Plus, now you keep the second. I didn't differentiate, so I don't need to tack anything on. Times the derivative of the first, which is just 10x. Now, I don't have to tack on anything here because the thing that I differentiated was in terms of x. All right, so that was that. Then I need to differentiate this guy using the power rule. So this is just going to be plus 4y. Need to tack on a dy dx because, yes, I differentiated this and it has a y in it. Equals 21 dy dx. That has a y in it. And then plus 0, which I'm not going to write. Okay, now what I want to do is I want to group my dy dx things that are stuck together on one side and everything else on the other, so that I can, end up like dividing everything out. So what I'm going to first do is I'm going to move this over to the right side by subtracting both sides by this. And I'm not going to write that 1 there, but I'm going to subtract that on both sides. And what I end up getting is 3x squared plus y 10x plus 4y dy dx equals 21 dy dx. And then we're bringing over this minus 5x squared dy dx attached there. All right, the last thing I want to bring over is this term that's stuck together. Again, I'm trying to group my dy dx's. So I need to subtract this guy from both sides. And I get 3x squared plus, I'm going to write this as 10xy. I just like that better. Equals 21 dy dx minus 5x squared dy dx minus 4y dy dx. All right, now at this point, all my dy dx's terms are on the right side. So what I can do is factor out a dy dx, because that's what I'm trying to solve for. And then everything, comes back on the inside besides the dy dx, right? So this becomes 21 minus 5x squared minus 4y. And of course, if we were to distribute that dy dx back in there, we would get exactly what we see above. All right. My last step is to divide both sides by this mess to get dy dx by itself, because that's my ultimate goal here, is to find the derivative. All right. So there we have it, folks. Dy dx in all of its glory. It's in terms of x and y, which we kind of expected here. But there it is. So if you're trying to find the slope of the tangent line to any point, x comma y, you can just plug in that x and y into this function, get the slope. All right, let's try this. So we want to find dy dx for ln x plus ln y squared equals 3. Well, remember, this was that special derivative. The derivative of ln of x is equal to 1 over x. Okay, that was a special derivative we learned a few videos ago. So the derivative of ln of x is 1 over x. The derivative of ln y squared, well, we need to use the chain rule because y squared is a function inside of the function ln of x. So how do we do this? Well, remember, we take the derivative of the outside, so it's going to be 1 over y squared times the derivative of the inside. So times the derivative of the inside, which is just going to be 2y, and then we tack on the dy dx. And that's going to equal 0, right? The derivative of 3 is just 0. So what I can do at this point is isolate my dy dx by first subtracting 1 over x from both sides. So I get, well, I'm going to actually simplify this thing a little bit just because I don't like it. This is just going to be 2 over y, okay? So this becomes 2 over y dy dx when I simplify. And then I have 0 minus 1 over x if I subtract that from both sides. And the last thing I'm going to do is I'm going to multiply both sides by y over 2 to cancel that out. And so dy dx is going to be negative y over 2x. All right, guys, I am going to stop here, but I'll see you guys in the next video. Thanks for watching. Hey guys, welcome back to the second part of this video, week 7 on implicit differentiation. So let's do some more examples. Alright, so we want to find dy dx for this function, e to the y cosine x equals 1 plus sine xy. Well, what I notice first on the left side is I have a product of functions, so I want to use the product rule here. Alright, so the product rule says keep the first times the derivative of the second. Derivative of cosine is negative sine. Alright, plus now you keep the second times the derivative of the first. Well, this derivative is in terms of y. So when I take the derivative of e to the y, which is just e to the y, I want to tack on a dy dx. Alright, so that's the left side. Now I want to take the derivative of the right side. So derivative of 1 is just 0, right? The derivative of sine of xy, I need to use a chain rule here because my outer function is sine, my inner function xy. Alright, so let's do this. So I want to take the derivative of the outside. Derivative of sine is cosine. Then I want to multiply by the derivative of the inside. Well, I got to use the product rule because this is a product. So the derivative of xy, keep the first, times the derivative of the second. Derivative of y is just 1. And remember, since we took the derivative of y, it's dy dx being tacked on. Okay, so keep the first times the derivative of the second, plus now you keep the second times the derivative of the first. Well, the derivative of x is just 1, and we don't have to tack on a dy dx because that wasn't a y term. So I'm going to write this a little bit clearer down here. Let's do this. Okay, equals cosine xy times x dy dx plus y. All right. So as before, I want to make sure that everything attached to a dy dx is on the side by itself. So what's attached to these things? Well, all of this is one attached thing. This is all one attached thing. So what I'm going to do is I'm just going to first subtract this business. Well, actually, I'll add it because if I bring that negative sign out to the front, it just becomes negative e to the y times sine of x. So I'm just going to get rid of this, I'm going to add e to the y sine of x to both sides. And then I'm going to move this cosine xy x dy dx over to the left side by subtracting it. Go ahead and subtract all of that. From both sides. And what I end up getting on the left side, I get my original cosine x e to the y dy dx, and then I get minus what I just subtracted, cosine xy x dy dx equals, let's see, y plus this e to the y sine x. All right, so now that I isolated my dy dx terms on one side, I'm going to go ahead and factor out that dy dx. And on the inside, when I factor that out, I'm left over with cosine x ey. Then over here, I'm left with minus cosine xy x. And then on the right side, I just have y plus e to the y sine x. And what I'm going to do is I'm just going to divide both sides by this mess, all of it, to get that dy dx by itself. Okay. And that is my derivative. That's dy dx. Right here. Dy dx. All right, let's do this. Again, we're just doing a bazillion examples so you get the hang of it. I encourage you to pause the video here and try this one on your own. Let's go ahead and do it. So when I take derivatives, I make sure that this is written to the 1/2, so I can use the power rule. Equals 1 plus x squared y squared. All right, so let's go ahead and differentiate the left side. I have to use the chain rule, and so I differentiate the outside, and I multiply by the derivative of the inside. Well, the derivative of x is just 1. The derivative of y is just 1 dy dx. All right? And you can write the 1 here if you want, but I'm not going to because it's just pointless. All right, so I just differentiate the left side. Let's do the right side. Now the derivative of 1 is just 0, so that's going to clear. Derivative of a product of functions, I need to use the product rule. Keep the first times the derivative of the second, plus keep the second times the derivative of the first. Okay, let's rewrite it a little bit neater over here. Well, actually, let's see, what am I going to do? Yeah, so I want to, again, group my dy dx stuff on one side. And so what I'm going to actually do is I'm going to distribute this thing just so that we can group our dy dx's in a nice kind of way. So I'm going to distribute that thing plus that same thing times dy dx. So there I go after distributing the left side. And then we'll write this as 2x squared y dy dx, just rearranging the letters a little bit, make it look better. And then we have 2y squared x at the end. Okay, so I'm going to group my dy dx's together. So what I'm going to do is I'm going to move this 2y squared x to the other side by subtraction. All right, and then I'm going to move the 1/2 x plus y to the negative 1/2 dy dx over as well. So maybe I'll just do this step by step just so you guys can see it. All right, so I did minus 2y squared x. Okay. All right, so next thing I'm going to do is this whole chunk is attached to the dy dx. So I'm going to subtract it all from both sides so that my dy dx terms are grouped together on the right side. Oh gosh, let's see how small I can write. Okay. Rewriting. So now I'm in a good position. Got my dy dx terms grouped. Oops. On the right side. And what I'm going to do now is, since I did that, I'm going to factor out the dy dx on the right so that I can do my division. I get that minus 1/2 x plus y to the negative 1/2. All right, factored. The left side just kind of chilling for a second. Okay, now my last step is to just divide by this mess. My hand is hurting from this problem. A lot of algebra going on here. Okay, and this is it, guys. This is the derivative. Now again, you're welcome to simplify this if you really want to, but I would advise against it because, things go wrong when you try to simplify too much. So this is dy dx, this mess that I circled in purple. I'm going to find the slope of the tangent to the curve of the point specified. So the point we're given is 1, 2, and the curve is going to be this implicit function that we have. So let's go ahead and differentiate because we want to find the derivative, and then after we do that, we want to plug in 1 for x and 2 for y to actually find the slope. All right, so the derivative of x to the third is 3x squared using the power rule. This guy is a product of two functions, the function 5x squared and the function y. So we need to use the product rule when we differentiate. So we keep the first times the derivative of the second, which is just 1 dy dx, plus keep the second times the derivative of the first, which is just going to give us 10x using the power rule. So again, I didn't tack on the dy dx here because that isn't I didn't differentiate anything with y in it. Okay, so that's done. Now this guy is going to be plus 4y. Again, I differentiated a y term, so tack on that dy dx equals derivative of 4y is just 4. And then we want to tack on the dy dx. And then the derivative of 11 is just 0, so I won't write that. Now, I want to group my dy dx's together. So what I'm going to do simultaneously is I'm going to subtract 5x squared dy dx as well as 4y dy dx from both sides. So that I group my dy dx terms together. Okay, so those clear. So what I'm left with is 3x squared plus 10xy, just rearranging that, equals 4 dy dx minus 5x squared dy dx minus 4y dy dx. And what I'm going to do at this point, since I've grouped all of my terms together on the right side, I'm going to factor out a dy dx. And what's left on the inside is going to be 4 minus 5x squared minus 4y. Now what I'm going to do is I'm going to divide both sides by this to isolate dy dx. Okay, and so this is the slope function. And what I want to do is I want to actually find a number for my slope, so that's where plugging in my point comes into play. I want to plug in 1 for x and 2 for y. So that's what I'm going to do. Plug in 1 for x and 2 for y. This is m over 4 minus 5 times 1 squared minus 4 times 2. So simplifying the top, we get, let's see, 23, I believe. And the bottom, we get 4 minus 5, which is -1, minus 8 is -9. So this is our slope of the tangent line to the curve at x equals 1, y equals 2. Find the equation of the tangent line to the curve at the indicated point. So this is just like when we had explicit functions. We need to figure out what is the slope, what is b. We're given a point, so we know that y equals -1, x equals 1, and remember our equation of a line is of the form y equals mx plus b. So let's first find the slope by taking the derivative. Okay, so we need to take the derivative of this guy. Now taking the derivative of the left side, I have a product of functions. So I keep the first times the derivative of the second plus keep the second times the derivative of the first. And then if I take the derivative of 1, that's just 0. Oops. Let's do that. Okay. So now I want to isolate dy dx so that I can find my slope. So I am going to write this like this. And then what I'm going to do is I'm going to subtract y squared from both sides to isolate the dy dx. And then I'm going to divide both sides by 2xy. And I end up getting a function for my slope, the derivative of y with respect to x. So this is m. And what we want to do, well, it's not m quite yet because we need to get a number for it, but you know, just like with the explicit functions, we're going to plug in our point at this point. So y, I'm plugging in -1 for y. I'm plugging in 1 for x and simplify. So my slope is going to be -1 over -2, which is just 1/2. All right, so I have my slope, it's 1/2, and now I can figure out what b is by plugging in everything that I have into my my generic slope-intercept equation. So we have y equals m times x plus b, And we're going to solve for b in the usual way. I'm going to subtract a half from both sides. So -1 minus a half is just going to be -3/2. All right, great. So I have everything I need. And so my equation, plugging in m and b, is y. Y equals 1/2 x minus 3/2. And that is my answer here. Okay, let's do one more like this. I believe that's the last example, yeah. So again, I'm in the same situation. I want to find the equation of the tangent line. So I encourage you to pause the video at this point and see if you can do it. So remember, I have, this is my equation of a generic line. I know y is 2 in this instance, and x is 4. And I need to find m by finding the derivative, and then I need to find b by plugging in x, y, and m into my slope-intercept equation. All right, let's do it. So taking the derivative of the left side, derivative of y squared is just 2y dy dx. The derivative of the right side, well, I need to use the quotient rule. So remember, the quotient rule tells me that the derivative of a quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. All right? So when I take the derivative of this, I need to apply this rule. So the top in this case is just x squared, and the bottom is xy minus 4. So the derivative of the top is just 2x times the bottom, which is just xy minus 4. Okay, and then I'm going to run out of room. Let's see. I guess I'll just write it over here. Let's do that. Okay, so there's my quotient rule. So I just did this part. Now I take the top and I need to multiply by the derivative of the bottom. Well, the derivative of xy minus 4, I have a product, so I keep the first times the derivative of the second, which is dy dx, plus, now you keep the second, times the derivative of the first, which is just 1. So that's the derivative of xy. Derivative of minus 4 is just 0, so I can just leave it at that. Alright, so now I have the numerator finished, and the denominator, I just have to do xy minus 4 squared, because that's g squared. Alright, now what I'm going to do is, let's see, what can I do here? What can I do? I want to isolate the dy dx, and it might be easier in this instance to just plug in x and y and then isolate dy dx. You know, because we kind of have a mess here, right? And so that's what I think I'm going to do here. I want to find dy dx, but I'm going to just plug in the numbers and see if that makes this a little bit cleaner. So what I'm going to plug in, I'm plugging in 4 for x, and I'm plugging in 2 for y. So let's see what happens. So I have 2 times y on the left. So that's 2 times 2 times dy dx. Okay. Then 2x, so I have 2 times 4 right here, times xy, 2 times 4 minus 4, minus x squared times x, so 4 times dy dx, plus 2. Alright, so there's my numerator, and the denominator is going to be, let's see, 4 times 2 minus 4 squared. All right, let's clean up this mess. So the left side I have 4 dy dx, doing the multiplication. And then I have this guy is just 8 times 8 minus 4, which is 4, minus 4 squared is 16, times 4 dy dx plus 2, all divided by 4 times 2 is 8, minus 4 is 4, squared is 16. Okay, so, alright, so now I can multiply both sides by 16 to kind of get rid of that. 16 and 4, yeah, 64. So this is going to give us 64 dy dx equals 32, 8 times 4. Then I'll distribute that minus 16 in there. So this is going to give us minus 64 dy dx, and then minus 16 times positive 2 is negative 32. Alright, so far so good. So now I am going to group my dy dx's together. So I'm going to add 64 dy dx to both sides. So 64 of something plus 64 of another thing. That's going to give us 128 dy dx on the left side. And I just have 32 minus 32 on the right side. And what I end up getting, oh my gosh, after all of this, I end up getting 0 on this side, on the right side. Then if I divide both sides by 128, I get dy dx equals 0, okay? So the slope is equal to 0, which is pretty annoying since we did all that work. I don't know, maybe it's not annoying, but... So our slope is equal to 0, and when our slope equals 0, remember, we just have this horizontal line. And so that means that, since y is equal to 2 and x is equal to 4 and the slope equals 0, that means that, we could actually just plug this stuff into y equals mx plus b just to make this a little bit more clear. Okay, so this is 0, this is 4, this is 2. So we get 2 equals 0 plus b, therefore b equals 2. So what's my equation? My equation is just y equals 2, because the mx is just going to go to 0, right, if we plug in 0 for m. So our equation is y equals 2. Pretty underwhelming. But there it is. So the equation of the tangent line to that curve is y equals 2 at 4, 2. And yeah, so that is it. That is going to be the gist of implicit differentiation. I hope this video was helpful for you guys, and thanks for watching. See you next time.